So imagine handing a hyperactive construction crew infinite steel,
Okay.
infinite glass, but absolutely zero blueprints. Like they are incredibly eager, right?
Great.
And they will build you a skyscraper in 5 minutes flat.
Oh, yeah, they're fast.
Fast, but when you walk inside, the stairs lead straight out a window, and the plumbing is hooked up to the electrical grid.
It's a disaster.
Exactly. And that is exactly what we're doing right now with AI in software development.
It really is a perfect analogy. I mean, we have these large language models, LLMs, that can just churn out thousands of lines of code in seconds.
Right.
We are essentially handing them infinite materials, but we're stripping away the architectural schematic.
We're just pointing at an empty lot and saying build.
Yeah, exactly. Build.
And what you get is a very fast, very spectacular mess. So, okay, let's unpack this. Today's deep dive is into this rather brilliant 2026 presentation by developer Luck036.
Okay.
And the title is Design Patterns in Modern C++ as Practiced Across 28 Header-Only Libraries.
Quite a mouthful.
It is, yeah. But our mission today is to explore this completely counterintuitive reality.
Right.
We're going to look at why decades-old software design patterns are actually becoming more important, not less, in an era where AI is writing our code.
Yeah, and this gets right to the heart of what the source identifies as the central AI paradox.
Okay.
Right now, AI makes code remarkably easier to write, but fundamentally harder to reason about.
Because there's so much of it.
Right, an LLM can generate just endless boilerplate, but it lacks high-level structural intent.
Yeah.
Like human engineers still have to provide what this analysis calls target shapes.
Target shapes.
Yeah, target shapes. Those are the classic architectural concepts like a strategy pattern or a builder pattern.
Right.
Those patterns have to act as the essential guardrails for the AI.
Because if you don't give the AI a strict vocabulary, it just hallucinates complexity, right?
Yeah.
It tries to invent a new way to build a door every single time it needs a door.
Yes, and that's incredibly inefficient.
So for anyone listening who is actively integrating AI into their, engineering workflow, knowing this vocabulary of patterns is your ultimate leverage.
Oh, 100%.
Because if you go into an LLM and prompt it to just, clean this up,
Yeah, you're rolling the dice.
you totally get to roll the dice. But if you say, hey, refactor this module as a strategy pattern, the results are exponentially better.
Right, because you get structurally sound, predictable code.
Right.
You're forcing the AI to compose from known mathematically sound patterns rather than just generating logic from scratch.
Okay, that makes sense.
The AI amplifies your engineering discipline, but it absolutely requires explicit scaffolding from you.
Right.
Human judgment stays in the loop because, pattern selection is a highly contextual design decision.
It's something the AI just can't do yet.
It simply cannot reliably make that choice alone. It doesn't know the future constraints of the system.
So if AI desperately needs these target shapes to function well without crashing our systems, what do those shapes actually look like in the wild?
All right, let's look at the actual code.
Yeah, the presentation takes us into the core architectural shape used across these 28 different industrial libraries.
Hmm.
It's their house style, I guess, and it revolves heavily around the strategy pattern.
It does.
Specifically, it explores something called the oracle pattern, which they use in the ellipsoid method for convex optimization.
Yeah, and the Oracle pattern is a beautiful application of strategy. If you look at these optimization libraries, you have a generic algorithm loop.
Okay.
That's the ellipsoid method. But here is the trick. The algorithm itself doesn't actually know the specifics of the problem it's trying to solve.
Wait, really? It doesn't know what it's solving?
No, it relies on a separation oracle.
Okay.
This oracle is a swappable component. Its only job is to assert whether a specific data point is feasible.
Okay.
And if that point is not feasible, the oracle returns a cut,
A cut.
right? Which is a separating hyperplane that slices the problem space in half, essentially telling the algorithm exactly where to look next.
Okay, I have to jump in here because this terminology is wild.
It is a bit dense.
Yeah, separation oracle and hyperplanes. Let's ground this. Why call it an oracle?
Well,
Is it literally just a mathematical magic 8-ball that the algorithm consults?
Yeah.
Like the algorithm shakes it and asks, oh, great oracle, is this data point valid?
That is actually spot on. It functions exactly like a mathematical magic 8-ball.
Seriously?
Yeah, the algorithm has no idea how to evaluate the data itself. It just asks the question, like, is this point X valid?
Okay.
And the oracle, which contains all the highly specific, complex domain logic, looks at the point and says, no.
No.
And here is the exact boundary, the cut where you went wrong.
Wow.
It hands the algorithm a new constraint.
And the power there is modularity, right?
Absolutely.
Because you can plug in totally different oracles without ever touching that core solver loop.
Exactly. You
Yeah.
could be calculating, linear matrix inequality feasibility,
Mhm.
or balancing a massive network flow,
Right.
or even designing a digital filter for audio.
Oh.
The core ellipsoid algorithm remains completely unchanged.
It just doesn't care.
It doesn't care what it's optimizing. You just hand it a different magic 8-ball depending on the job.
Okay. That level of modularity is incredible. But what about the performance cost? Because in my experience, usually when you make software that flexible and generic, it slows down.
It gets heavy.
Right. The machinery gets heavy.
Yeah.
But these libraries are obsessed with speed.
They have to be.
So they contrast how this strategy pattern is applied at compile time versus runtime.
Yes.
For compile time, they use templates, like this game memory thing in the ACPTN library.
Mhm.
But for runtime, they use virtual dispatch, like in their delay calculator, where they are swapping between linear and Elmore delay models on the fly.
And that distinction, that is the absolute bedrock of modern C++ development.
Really?
Yeah. So look down the mechanics. Virtual dispatch is great because you can swap these strategies, these oracles, while the program is actively running. The trade-off is that it requires what's called a vtable, or a virtual method table.
Okay, pause. What exactly is a vtable?
Well,
Because I hear that thrown around like a dirty word in performance optimization.
it essentially is a dirty word when you're chasing microseconds.
Right.
Think of a vtable like a physical directory in a massive office building.
Okay.
Every single time your program wants to run a command, it can't just run it.
It has to look it up.
Exactly. You have to walk over the directory, look up the command, find out which floor and room it's supposed to go to, and then execute it.
That sounds exhausting for the computer.
It adds a layer of pointer indirection. It's like stopping to ask for directions at every single intersection.
Okay. Yeah.
It slows down execution. Templates, on the other hand, constrain the strategy at compile time.
So before the program even launches.
Exactly. The compiler looks at the code and says, I know exactly which oracle we are using here.
Oh.
Because it knows the exact destination in advance, it doesn't need the directory.
It skips the lobby entirely.
It skips the lobby. It can inline the code completely, meaning it just drives straight to the destination without stopping.
That is beautifully simple.
Right. So the rule of thumb in these libraries is use templates to drive straight there when the strategy is known at compile time.
Okay.
Only use a vtable, only stop and ask for directions when the strategy absolutely must vary dynamically at runtime.
Which perfectly transitions us to how modern developers are squeezing out every single ounce of performance.
Right.
Because logic is just the engine, but you need to optimize the transmission.
Absolutely.
And since we just touched on the raw speed of compile time templates, the author takes us into some uniquely complex C++ structures to avoid those vtables entirely.
Yeah.
Specifically, CRTP, the curiously recurring template pattern.
CRTP.
Hmm.
It is one of those concepts that sounds incredibly intimidating,
It really does.
almost like an esoteric academic theory.
I was going to say it sounds like a spell from Harry Potter. Curiously recurring template pattern.
It really does sound like magic, right?
Right.
But it solves a very practical, brutal problem.
Okay.
It allows for what we call static polymorphism,
Right.
meaning you get all the benefits of an inheritance hierarchy. A base class provides shared, reusable logic to derive child classes.
Sure, standard object-oriented stuff.
Exactly. But you get that without the vtable slowdown we just talked about.
You really?
It keeps everything fully inlineable and lightning fast.
Okay, wait. Break that down for me. How do you get the flexibility of a parent passing traits to a child without the child having to constantly check the vtable directory to see what it inherited?
Right. So to understand how it avoids the vtable, you have to look at how it's structured.
Okay.
In normal inheritance, the parent class doesn't know anything about the child.
Right.
It just exists, and the child inherits from it later.
Okay.
That unknown relationship is why you need the vtable directory at runtime.
Uh-huh.
But in CRTP, the child class inherits from a template of the base class, and it passes itself as the template argument.
Oh, wow. So let me try an analogy here.
Go for it.
It's not a parent passing traits down. It's more like a factory that prints a customized instruction manual for a specific machine.
Okay.
But instead of printing a separate book that the machine operator has to stop and read, which would be the vtable,
Right.
the factory prints the instructions directly onto the actual gears of the machine itself.
That is a phenomenal way to visualize it, yes.
Oh,
The base class, the factory, knows exactly what the derived class the machine is going to be before it's even finished compiling.
that's crazy.
It embeds the logic directly into the gears.
Uh-huh.
There is no separate book.
So no V-table.
There is no V-table. The compiler monomorphizes it.
Monomorphizes.
Yeah, meaning it generates a unique, highly optimized, direct version of the code for every single specific machine type.
That is brilliantly efficient.
It is. And if we connect this to the bigger picture, it proves that this kind of architecture isn't just some weird C++ quirk.
Right, because other languages must deal with this too.
Exactly. The author explicitly compares CRTP to Rust.
Ah, Rust.
Now, Rust is a newer language that notoriously has no inheritance at all.
Right. Yeah.
Therefore, it cannot have a literal, curiously recurring template pattern.
Because in Rust, you don't have parents and children, you have traits.
Exactly. But Rust replicates this exact same zero-cost, no fee-table static dispatch.
Really? How?
It just uses the self keyword and associated types to do it.
Oh,
It achieves the exact same goal. The logic is printed directly onto the gears.
so it's a universal problem.
Yes. The fact that entirely different programming languages are inventing totally different syntax to solve this exact same problem proves that this pattern isn't a stylistic choice.
Right.
It is a universal fundamental need in high-performance computing.
Okay, so knowing how to process logic quickly using oracles and CRTP is great, but logic is just the engine. What about the fuel?
The data.
Yeah, how do you structure the massive chaotic amounts of data flowing through these 28 libraries? Because processing speed means absolutely nothing if your data structure is a tangled mess and the CPU just, checks on it.
Absolutely. And that brings us to how they handle data scaffolding, specifically through structural patterns.
Okay.
If you look at the code, they rely heavily on the builder pattern, most notably in a structure called the CSR graph.
Yes, the CSR graph. I actually love how they apply the builder pattern here.
It's very elegant.
They completely separate the construction of an object from its final representation. With this graph, they use a builder object to keep the construction incremental and extremely fast. They note its O of one-time complexity on the outside,
Right.
which basically means it's instant no matter how much data you throw at it.
It's just buffering it.
Yeah. But once it's done building, the internal result is this compact, highly cache-friendly, completely immutable object.
And the cache-friendly aspect is what's really crucial there.
Why is that? Why does it matter so much that it's cache-friendly once it's built?
Because fetching data from the computer's main memory, RAM, is agonizingly slow from the perspective of a CPU. It's like a chef having to walk down the street to the grocery store every single time they need a pinch of salt.
Oh man, yeah, that would take forever.
Right. A CPU cache is the little shelf of ingredients sitting right on the chef's cutting board.
Oh, okay.
By making the final CSR graph compact and contiguous, meaning all the data is packed tightly together in a neat row, the CPU can load the whole chunk onto its cutting board at once.
That makes so much sense. So, as you said, you get the messy, easy flexibility while you're building the graph,
Right?
but you get pristine, lockdown, blistering performance when you're actually analyzing it.
Exactly.
And what happens when the data itself is messy?
What do you mean?
Like when you are dealing with a bunch of diverse, different data types within those structures, the source highlights type erasure using STD variant.
Yes, they use STD variant for what is known as sum type polymorphism.
Whoa, okay, pause. Some type polymorphism, you just completely lost me. Are we talking about adding numbers together, or is this something else entirely?
Fair question. No, it has nothing to do with math. Let me translate that.
Please.
In older object-oriented programming, if you had a bunch of different data types, say a circle, a square, and a triangle,
Okay.
you'd create this massive, sprawling family tree of inheritance to group them together.
Right, like a shape-based class.
Right. That's an open-ended hierarchy.
Yeah.
Sum type polymorphism is completely different. It basically means you have a fixed menu of options.
Okay.
You're declaring this variable can be a circle, a square, or a triangle, and absolutely nothing else.
Ah, so instead of an endless buffet of messy family trees, it's a closed menu.
Exactly.
Yeah.
And because it's a closed, known set of types, STD variant is vastly superior to the inheritance tree
Why is that?
because it's exhaustive, meaning the compiler can check to make sure you handled every possible option on the menu.
Oh, that's safe.
Very safe. It's also stack allocated, which means it sits right there in local memory rather than being scattered all over the heap.
Right.
And once again, because we know all the options up front, it completely avoids that dreaded vtable directory lookup.
Right, so we're skipping the lobby again.
Skipping the lobby every time.
Love that. We should also touch on the memento pattern here, which they use in their FM partitioning algorithm. Memento is essentially a snapshot and restore function.
Right, it's a formalized undo button.
Exactly. The author shows how the algorithm uses it to backtrack when a move yields a negative gain.
Mhm.
So, for example, if the algorithm is trying to optimize a network and it moves a node from group A to group B, but suddenly the network efficiency drops,
That's a negative gain.
right. Instead of having to painstakingly reverse the complex math of that bad move, it literally just reverts to a saved memento, a snapshot of the previous state.
Right.
It is a dedicated undo button for just terrifyingly complex math.
And we really need to understand why that undo button is vital. Like, we have to look at where this code is actually being deployed.
Yeah.
We aren't just talking about academic theory here.
Yes. Because we've talked about all this hyper-optimized code, the engines, the fuel, the memory management, but where does it actually run?
Right.
The presentation moves us from theory into the very physical world of electronic design automation, or ED.
ED day.
Yeah, this is the industrial software used to design actual computer chips. Every single pattern we've discussed powers tools like OpenRoad or Yosys.
And designing a modern microchip is arguably one of the most computationally intensive tasks humans undertake.
It's mind-boggling.
It really is. We're not talking about laying out a simple circuit board. We are talking about mapping billions of individual transistors,
Billions.
billions, microscopic timing paths, and geometric layers down to the nanometer. The sheer volume of data required to simply hold a modern chip design in a computer's RAM is staggering.
And here's where it gets really interesting.
Yeah.
The author brings up the flyway pattern for exactly this reason. On a computer chip, you might have 50 million cell instances, say 50 million identical logic gates. They all share the exact same intrinsic state. Their physical geometry, their timing arcs, their power usage, it's all identical.
Right, they're identical parts.
So instead of saving 50 million copies of that data, that shared intrinsic state is stored in just a few thousand cell masters.
Ah,
The only thing that changes for the 50 million instances on the chip is their extrinsic state, which is basically just their specific X and Y coordinate on the silicon.
right.
So, wait, let me make sure I'm grasping the scale of this.
Sure.
Without the flyweight pattern acting as this master instance backbone, would the software just completely run out of memory trying to map every single transistor? Like, would the system literally crash?
It absolutely would crash.
Ah.
And not just eventually, it would crash almost immediately.
Hmm.
The machine would run out of memory before you even finished loading a fraction of the design.
Just from opening the file, basically.
Yeah. Storing the complex geometric polygon data for a single transistor 50 million times over would exhaust any supercomputer's RAM. By storing the master blueprint once and having 50 million incredibly lightweight instances, merely point to that master and say, I am that shape, but I live at coordinate XY.
Yeah.
The memory footprint shrinks by orders of magnitude.
It's like the difference between architecting a million individual, highly detailed houses in a database versus saving the blueprint for one house and then just handing out a million street addresses.
That is exactly it. And that same flyweight logic applies to vias, rule decks, and timing arcs across the entire EDA pipeline.
Wow.
This is the essence of why these design patterns matter. They aren't just academic exercises to pass a code review.
Right.
They are the literal, physical, structural scaffolding that allows human hardware design to scale down to the atomic level.
That's incredible.
Without the flyweight pattern, Moore's law stops dead in its tracks because we wouldn't have the software capable of designing the next generation of chips.
Okay, so we've taken this grand architectural tour of the patterns they do use, but as we start to pull this all together, we have to look at the author's honesty slide. Yes.
Because sometimes what an engineer deliberately chooses not to use tells you way more about their fundamental philosophy than what they do use.
Definitely. What's fascinating here is the sheer uncompromising pragmatism.
Yeah.
The source lists several classic textbook design patterns that are explicitly, purposely avoided in these libraries.
Okay.
The first one is the PIMPLE pattern, which stands for Pointer to Implementation.
Pimple. Great name. I know Pimple is usually used to hide the ABI to keep compile times down.
Right.
But what exactly is an ABI and why do they not care about hiding it here?
So ABI stands for Application Binary Interface.
Okay.
It's basically the boundary between compiled pieces of code. Usually you use Pimple to hide your private, messy implementation details behind a clean pointer.
So if you change the messy details, the rest of the program doesn't have to recompile.
Exactly. It saves time. But remember the title of this deep dive? These are 28 header-only libraries.
Ah, so they are shipped as raw source code. Exactly. There is no precompiled binary boundary to protect. The user compiles everything themselves.
I see.
Therefore, going through the trouble of hiding the ABI with a Pimple pointer just adds useless overhead. So Pimple is thrown out.
They also completely abandon the null object pattern.
Right.
In the past, if you had missing data, you'd create a dummy null object just to prevent the program from catastrophically crashing when it tried to read something that wasn't there.
Right.
But they've replaced that entirely in favor of modern C++ plus STD optional.
Which is a massive upgrade in safety.
Like so.
A null object prevents a crash at runtime, but STD optional forces the compiler to acknowledge that the data might be missing before the program even runs.
Oh, wow.
It's the difference between catching a mistake on paper versus catching it when the engine's already running.
That is way better.
Yeah, they also explicitly avoided the observer pattern.
The observer pattern, that's where objects subscribe to updates and watch each other, right?
Yes, and while it sounds nice in theory, in practice, it can create a tangled, impossible to debug web of dependencies.
Just a mess.
You never know who is watching who.
Right.
Instead of that mess, they simply use a single straightforward logging facade to track what's happening.
Keep it simple.
Exactly. The ultimate design decision rule the author lays out for modern C++ is this.
Okay.
Choose the cheapest abstraction that still expresses the intent.
Choose the cheapest abstraction that still expresses the intent. If you take away nothing else, that is a mantra every developer should have written on a sticky note attached to their monitor.
Seriously.
So what does this all mean? Let's zoom all the way back out.
Okay.
We started with this paradox of AI writing our code, acting as an incredibly fast construction crew that lacks blueprints.
Right.
We went deep into how oracles use magic 8-ball logic to drive generic algorithms. We looked at how CRTP prints instructions directly onto the gears to achieve static polymorphism without those slow vtable directories.
Skipping the lobby.
Skipping the lobby. We saw how builder patterns and the closed menus of SD variant cleanly structure massive data.
Yeah.
And we realized that without the flyweight pattern acting as a master blueprint, the software designing our modern microchips would literally buckle under its own memory weight and crash.
Almost immediately.
Immediately. And through all of this, we discovered that these patterns aren't just legacy textbook terms.
No.
They are the essential human vocabulary that keeps the machines on track.
And this raises a massive, almost existential question, though, and I think it's where we have to leave the listener today.
Oh, okay.
The author explicitly states that AI makes pattern selection a design decision AI can't reliably make alone.
Right now.
Right now, exactly. Right now, the AI needs our human blueprints. It needs our vocabulary.
Right.
But as large language models continue to evolve, and as they ingest, analyze, and test billions of lines of code at a scale humans can't even comprehend,
Yeah.
is it possible that AI will eventually invent entirely new, highly efficient structural patterns?
Oh, wow. Patterns that we didn't invent.
Yes. Patterns that are perfectly optimized for silicon machines, but completely unreadable to the human eye.
That is wild.
And if that happens, we face a massive choice as a species.
Yeah.
Will we force the AI to stick to our legacy human patterns just so we can stay in the loop and read the blueprints?
Right.
Or will we have to swallow our pride, step back, and learn to read the AI's native design patterns?
Wow. A fascinating tension between human legibility and ultimate machine native optimization.
Truly.
Something to definitely think about the next time you sit down, open a prompt, and ask an AI to write a script for you.